Thanks for having me here. So I work on computer vision, and computer vision is about understanding and extracting meaningful content from images. And there are many interrelated, but at the same time quite technically different computer vision problems, like image recognition, for example, as in ImageNet competition, object detection, where you want to detect an object, object part localization, which is also known as pose estimation, semantic segmentation, you want to assign to each pixel in the image a class label based on the object that this pixel belongs to. 3D reconstruction, you want to reconstruct the shape of an object. And of course, high-level analysis tasks like activity and behavior recognition. So in my work, I'm working on all these problems with a special, with a footnote that my focus is on an object of a special interest, and that's basically humans. Okay, so the aim of my work is to analyze humans, in particular the human body and the human face, in completely unconstrained images and videos. And of course, if you can do that, there are many and exciting associated applications in health, economy, entertainment, as well as in related disciplines like human-computer interaction and robotics. So, so in this talk, I will be talking about the face analysis pipeline, which is basically a computer vision system built exclusively for the human face. And the focus of this presentation will be primarily on what has been achieved on the various face analysis tasks after the advent of deep learning. So I will be definitely talking about the first 4 tasks: face detection, landmark localization, facial part segmentation, and 3D reconstruction. And then, if time permits, I will also say a few words about face recognition. So the first task in the face analysis pipeline is face detection. And of course, to analyze a face, you want first to detect it in images and videos. And most people in the community think that face detection is a fairly solved problem. And the reality is not very far from that. And actually, face detection has been one of the earlier successes of computer vision back in the late 90s with Viola Jones' face detector. And for many applications, face detection works really, really well. Even on your mobile phones, you have software that can detect your face pretty accurately and almost in real time. However, what would happen if I ask you to detect all the faces in these kind of images? Is this something that current technology can really deal with? And notice that you don't only want to detect the face, but you want the system to reject all the background clutter. You don't want to have false positives into your system. The second task that is typically part of the face analysis pipeline is called facial landmark localization. So the task, the aim here is to localize a set of predefined landmarks or fiducial points on the human face, and these landmarks are predefined and have some sort of semantic meaning. So for example, there are landmarks for the tip of the nose, the corners of the mouth, the corners of the eyes, the eyebrows, and so on. And this task is also called as, is widely known as face alignment. And the reason for that is that you can use these landmarks, or a subset of these landmarks, to bring the face into some sort of canonical reference frame, which then facilitates higher level recognition tasks like face recognition and facial expression recognition. And the simplest of this kind of alignment is basically to use some of these points to remove scale, rotation, and translation, to remove similarity transformations. Now, the focus in face alignment over, let's say, the last 10 years has been on 2D face alignment. So you just want to localize, to estimate the x and y coordinates of these landmarks on the image plane. But very recently, there is a lot of interest in 3D face alignment, where in addition to the x and y coordinates, you also want to estimate the z coordinate. So get like an estimate for the depth, which gives some more information about the structure of the face. Another interesting task in the face analysis pipeline is called facial part segmentation. And the aim here is to assign to each pixel a class label based on the facial component that this pixel belongs to. And here on the right, you can see that we have 7 facial components plus background. So in total, we have 8 classes. And this is basically a semantic image segmentation problem. Now, the obvious way to do face alignment is, to do facial part segmentation is to do face alignment. So use any of the methods, any of the existing methods for face alignment to detect these landmarks, and then basically connect the landmarks. And then you can get a very good estimate of the facial components. And this is actually how we create the data sets for facial part segmentation. Because there is like a very large number of data sets, thousands of images, which have been annotated in terms of facial landmarks, then we just go on and connect the landmarks and create these masks that you may see over here. And of course, the obvious way to approach this problem is to do facial alignment and connect the landmarks. However, and as I will show you later, if you treat the problem as a facial part segmentation, then you get better performance. Okay? That's indeed a semantic image segmentation problem. Face alignment does not suffice. The last of these these low and mid-level face analysis problems is called 3D face reconstruction. And most people don't know much about this problem. The aim here is to recover the full 3D facial geometry of in terms of XY coordinates, XY and Z coordinates of the human face. This is also called the 3D facial shape. Now, if we are restricted to a sparse set of landmarks, then this is equivalent, is exactly the same as 3D face alignment. Yes, so. Okay. So finally, we have another of high-level analysis tasks. And the first of these tasks, which is perhaps the most popular, is face recognition or face identification. And the setting here is given two facial images, we need to tell whether they belong to the same person or not. So that's the most common setting for face recognition, and that setting is basically called face verification. And that's the kind of problem that they're solving at Heathrow Airport. Okay? Another very interesting and quite popular problem is facial expression recognition. And the task here is to classify a facial image in terms of some sort of emotions. If, for example, the person is happy, surprised, and so on. And a related problem to that, which has also received quite a lot of attention, is to detect the movement of the facial muscles. And that's called facial action unit recognition, and that's, I would say, is more like a computer vision problem, because basically you have to detect something that moves from data, and there is no link between expressions and emotions as there is in a facial expression recognition problem. A related problem to facial expression recognition is facial attribute classification, which is basically about classifying facial attributes like makeup, glasses, hair, lipstick, and all that stuff. There are also other face-related tasks not mentioned here. For example, people have been working on face super resolution, which aims to increase the resolution of low-resolution facial images, age and gender classification, which to some extent can be considered a sub-problem of facial attribute classification, facial performance transfer, and lip reading that we have been talking about. A few years ago, all these problems would be dealt with the standard computer vision pipeline, which basically consists of some sort of feature extraction. So you start by extracting hogs, SIFT, or LBP features, whatever features you like. And then on top of that, you use your favorite machine learning. And if you can be a little inventive about the method, have some intuition about the problem that you want to solve, you can have a very good publication. Now, following the success of deep learning in various computer vision problems like classification, image classification, detection, pose estimation, and so on, all these problems now are dealt with deep learning, and that's going to be the main focus of the presentation. So it's not my intention to provide some sort of overview of deep learning and convolutional neural networks. What I will quickly do is give a brief description of ResNet. So ResNet is the prevailing CNN architecture currently used in computer vision, and I think it's gonna be that for a long time. Here is one version of ResNet, like a simplified version of ResNet, and the way that it works is, as in all convolutional architectures, the image is processed by a series of convolutional layers, nonlinearities, and max pooling layers. Now, in ResNet, most of the max pooling has been replaced by convolutions. So if you want to reduce the dimensions of the image by 2, then basically instead of doing max pooling, you just do a convolution with a stride of 2. And in that way, max pooling is somehow learned instead of just doing the standard max pooling operation. So all these operations can be grouped together. For example, this particular version of ResNet has like 5 groups, and within each group there are some building blocks, and each of these groups works at a particular resolution. Okay, so for example, this group over here, its main building block is 3 convolutional layers. The first is a 1x1 convolution with 64 filters. The second is a 3x3 convolution with 64 filters. And the last is a 1x1 convolution with 256 filters. And we have 3 of these building blocks, okay? One after the other. And this works at half resolution compared to the original image, because that's the input to that block. Okay. Now, in ResNet, in addition to the convolutional layers and the nonlinearities, there are also skip connections, which connect the input with the output. And as it was shown in the ResNet paper and experimentally verified by hundreds of other researchers, this very simple addition basically makes the training of the network a lot easier. So with this kind of trick, you can just go on and train very deep or very wide neural networks. Okay, so neural networks with a lot of parameters. Another thing that is worth mentioning is that in the latest version of ResNet, the nonlinearity, the ReLU nonlinearity precedes the convolutional layer. Okay. Now, the basic building block, the residual block described in ResNet is on the left, and following that, there are other variants have been proposed. So, for example, that's ResNet X, which was published at CVPR 2015, and the difference is that basically there is a split in 32 different branches. Each of these branches process only using a small number of filters, 4, and then the result is reassembled in the end. That's a more flexible configuration, and it's shown to give better results. In a paper that will appear in the forthcoming ICCV, information is processed in a hierarchical manner with a series of multi-scale convolutional filters of increasing spatial support. And to see this, observe that the output of the first convolutional layer is used as input to the second one. And because of that, the effective kernel size of convolution is basically 5, okay? So this is equivalent to processing information with a filter size of 5 by 5 at this level and 7 by 7 at this level. So information is processed hierarchically in a multi-scale fashion. But the real important thing to notice is that all these architectures have skip connections. Okay, so input is connected to the output. So let's now turn to face detection, which is the first of the tasks in the face analysis pipeline. And for many years, the standard benchmark that people have been using is FTDB, has been FTDB, and it's still FTDB. These are some images taken from the FTDB, and as you may see, FTDB is a fairly difficult data set. There are faces in different poses, as you may see here and here, faces in very different scales. So observe these tiny faces in the background, faces occluded by other faces. In some cases, large amounts of occlusion. There are also facial expressions. In other images, there are also some illumination variation. So it's a fairly difficult data set, and before the advent of deep learning, that's the kind of performance that you would get on that data set. So that's more or less up until 2014. So every year there would be a new paper, but with a new idea. But the improvement in total was really, really small, and progress has been quite slow. So that's before deep learning, and that's basically after deep learning. So in 3 years, we managed to get from that to this. So basically, deep learning methods saturated or nearly saturated FTDB. And of course, it's not exactly 100% accurate, but in that data set, as also in most computer vision data sets, you cannot get 100% because the labels are, well, there are labels which are incorrect. So there are many faces in the FTDB images which were not annotated. And if you have a very good system that can pick up these faces, these will be taken as false positives. Okay, so you will never get 100%, but it's obvious that we're very close to saturating that data set. Nevertheless, still people report results on this data set. I don't think that there is a face detection paper that don't report results on FTDB. So, because FTDB started to become saturated, then some people came up with a wider face. And that's a very good paper, and an oral paper at CVPR last year. And that's a really large-scale data set. So that's something like 30 or 40 times bigger than FTDB. And the data set is split in 3 partitions: easy, medium, and hard, with easy already being a lot harder than FTDB. Okay? Initially, right after the release of that data set, it was believed that this is really a difficult data set. And why is that? Because even methods based on deep learning struggle on that data set. So with light blue is the first deep learning approach that was trained and then tested on that particular data set. But then that was in 2016. Okay, the dataset was released a bit earlier, 2015. I think the archive version came out. And then let's say in 2 years, from that we get this, this, and this, with better deep learning architectures. So it seems that basically the easy and medium split have been more or less saturated, or they are very close to saturation, and there is some good research potential only for the hard partition. Okay? And the hard partition of wider face is really, really hard. You must detect faces in images like this. Also, the image that I showed you in the beginning was taken from wider face. So it's a really, really difficult problem to make some improvement on this kind of images, taking also into consideration that there is a labeling noise that you have to deal with. So what's like a good architecture for face detection? So it turns out that all you need to do is take the state-of-the-art method for object detection, tweak it a bit, train it on that dataset, then test and see what happens. So the state-of-the-art architecture for object detection is called faster RCNN. And face RCNN is basically a variant of that architecture and is the yellow curve in these figures. So it's one of the best methods on this data set. So this face RCNN or faster RCNN basically consists of three parts. The first part is a deep convolutional neural network, and you can use a ResNet for that. And then there are two branches. The first of these branches is called region proposal network, and then that's the upper branch, and then the lower branch is called fast RCNN, which is the previous version of faster RCNN. So the way that it works is that this deep convnet produces some convolutional features at this point, which are then used as input to the region proposal network, the job of which is to propose some regions in the image which are likely to contain faces. And then once these region proposals have been generated, then they are fed to the lower branch, which is the fast RCNN. And the fast RCNN works like this. Because these regions will have different size, you have to somehow come up with a fixed length representation to do classification or regression. So what you do is you basically divide these regions in a fixed number of cells, and then for each of these cells you do a pooling. So that's why this is called region of interest pooling. And after you do that, after pooling, you get like a representation of fixed length. And then you can use fully connected layers to do classification for face detection, and also bounding box regression, and that will adjust the proposals generated by the region proposal network. So that's how it works. Okay, let's now turn to the second task in our pipeline, which is about facial landmark localization. And prior to deep learning, in general, it was the face alignment problem was considered relatively solved for frontal faces. Some example of these faces you can see here at the bottom. I think methods work equally well for some more difficult images like this, with more occlusion, with a little more pose variation. However, maybe with more difficult illumination, so these are not really big problems. The real problem was pose, and for large poses the performance of these methods were quite poor. Okay, another issue is that if you go to extreme poses, you have like profile faces, then you will need different models. So you will need a model for frontal faces and a model for profile faces. And also there was very little work on 3D face alignment. Okay, so with deep learning, we can now do full 3D face alignment, which, if you remember, is also about estimating the Z coordinate. Okay, along with the X and Y coordinates, you also want to estimate the Z coordinate. And now, in addition to this additional step that you have to take, there are some important differences between 2D and 3D face alignment that are worth of mentioning. So in 3D face alignment, the whole spectrum of facial poses are considered, and this immediately implies that there will be images with large amounts of self-occlusions. Okay. Also, in 3D face alignment, all landmarks must be localized, not just the visible ones, which is the setting for 2D face alignment, where you have different models to handle profile and frontal faces. So the reason for having different models is that you estimate different landmarks. Okay, in 3D face alignment, you must estimate all landmarks. So for example, in these two images, you also have to estimate the landmarks in red, which are basically the self-occluded landmarks. And finally, 3D face alignment treats the object as a three-dimensional object. And basically, what happens, what this means, is that the landmarks must be localized on the image based on where they would be projected if there was no self-occlusion. So you don't try to track the boundary, which is the standard thing that you want to do in 2D face alignment. Okay, and that seems to be a bit harder, but it comes with a very nice property that basically you can have landmark correspondence across the whole spectrum of facial poses. So, what's a good architecture for face alignment? It turns out that what you can do, at least in terms of estimating the X and Y coordinates first. So to estimate the X and Y coordinates, what you can do is basically take a state-of-the-art architecture from human pose estimation, which is the problem of localizing the parts of the human body. Train it on face alignment datasets and then test. Okay? So if you do that, then basically you can almost saturate almost all 2D face alignment datasets. So what I show you here, so the performance of that network is the blue curve. What I show you here is the performance on 5 different test sets. And these test sets are completely disjoint from the training set. So we're talking about cross-database experiments only, okay? And blue is the performance of the deep learning method. black is not the performance of the method on these datasets. Black is the performance of a state-of-the-art method from CVPR 2016 applied on the easiest 2D phase alignment dataset. So we just ran that method on that dataset, and then on that dataset there is extremely little progress over the last few years, and it's a dataset that it was already saturated before deep learning. So we said that's how far you can go in a 2D phase alignment, right? So then we ran that method, we got the curve, and then we just copied the curve, we superimposed the curve on these figures, okay? And you may see that in all data sets, the blue and the black curves are almost one on top of the other. There is only one exception, which is this data set. And what happens in this data set is that actually the annotations are not very accurate. So we inspected the larger errors produced by the network based on the ground truth, and we found that the network predictions were more accurate than the ground truth. So, and the truth is that the ground truth has been produced in a semi-automatic way. So it kind of makes sense that for this particular data set, the quality was not particularly great. So the state-of-the-art architecture for human pose estimation that we used for our experiments is described in this very good paper called Stacked Hourglass Networks for Human Pose Estimation, and that was published in last year ECCV. And so this is the architecture for the hourglass network, and it basically has three features, three main characteristics. The first of these characteristics is that it's a residual based architecture. So all the building blocks you may see here basically are the residual blocks or groups of residual blocks that we saw before. They contain skip connections, okay? And that's the first feature. The second feature is that this architecture is a fully convolutional architecture, which means that it can make predictions at pixel level, and basically comprises two parts. So the first part is the top-down part, so from here to here, which is basically very similar to ResNet. And then there is a bottom-up part, which is from here to here. And in that part, information is analyzed by these blocks, and spatial resolution is also recovered. And there are two ways that you can recover spatial resolution. One is by just upsampling, and the other is by using deconvolutional layers. Now, the third characteristic, the third feature of this architecture is that as we go all the way up, so from here to here, information from the top-down branch, top-down part of the network is reanalyzed here, 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 and here, and then reused to go all the way up to the original resolution. And this helps the network making a lot more accurate predictions. So you are reusing features, reanalyzed features from the top-down part of the network. So that's the hourglass architecture. And to train an hourglass architecture for human pose estimation or for phase alignment, you can use what is called heat map regression. So what you do is that at the output of the network, you have k output channels, each for each landmark. So if you have like, for face alignment, we have like 68 landmarks, we have like 68 channels. And each of these channels corresponds to a landmark. So in particular, what we do is we place a Gaussian at the x and y location of the corresponding landmark. Okay, so each landmark is basically encoded by a Gaussian centered at the x and y coordinates of that particular landmark. Okay, and then we train the network to regress these heat maps, and from the maximum of the regressed heat maps, we can get the location of the landmark. And so these heat maps basically are represent confidence maps. Okay, so the network is trained to produce some confidence maps about the location of the landmarks, and training is used with standard L2 loss, but applied at the pixel level. Okay, so for each pixel you calculate an L2 loss. Now, this kind of idea, the heat map regression, has been shown to be a lot better than trying to predict directly like a vector which contains all the coordinates of all landmarks. Okay? So it's quite common to do that in landmark localization. Another very nice feature that comes with heat map regression is that you can take these heat maps generated by the network and then stack them with the image, okay, and then use them as input to another network, same architecture, that will refine the location of the provided by the first network. Okay, so what happens is that this confidence produced by the first network is used to guide the prediction of the second network. So for our experiments, we use the stack of 4 hourglass networks. Okay. And with the exception of the first one, all the others are guided by the heat maps generated by the previous network. And then, if you do that, then up to this point you get some heat maps, and from the location of the maxima of that heat maps, you can get the location of the landmarks. Then what we did was to stack these heat maps with the image, and then pass them through a ResNet. And then we can also, in that way, we can also estimate the Z coordinate. So we broke down the 3D estimation problem into 2 subproblems. The first is basically to estimate the X and Y coordinates, and then the other is to estimate the depth, given that we have the predictions of the X and Y. And some confidence scores coming with them. And if you do that, you can get really, really good performance across the whole spectrum of facial poses. And as you may see here, and you can also get resilience to all types of noise that you can imagine, occlusion, expression, illumination. To some extent, the network is resilient to low face resolution. And I have a video that I want to show to you. So, so in that video, there is no tracking involved. So we just do detection per frame. Okay, I think that's enough. So each of the faces is like fitted separately, okay? So let me go back. There is also code that you can download. So we provide full training and test code. So you can reproduce everything that we have in the paper. So you can get it from that link. Oops. Okay. So another interesting face analysis task is facial part segmentation. And similarly to face alignment, this has been a task in which there has been some good performance, but mainly for easy faces with little pose variation. So on the third column, the results are pretty good, but that's basically the ground truth. So what the actual results of that method are, you can see them in the second column. And you may see over here that with some little pose variation, then the method breaks. Okay? And again, with deep learning, we can now segment very difficult faces in arbitrary poses, expressions, occlusions, as well as illumination. And so these are some results that we got by applying deep learning for this kind of problem. And so what's a good architecture for facial part segmentation? Well, it turns out that one can reuse this kind of hourglass network that I talked about before, or any type of convolution, deconvolution architecture. So you can just take that network, then train it for semantic segmentation with 8 classes for this particular case, and get very nice segmentation masks, and it works quite well if you do that. What we did in this paper was basically to guide segmentation with face alignment. And why is that? Because face alignment is an easier problem, and once you have the landmarks, then that's really useful information to guide the segmentation network. So that's the first of these networks produces the facial landmarks, and so it's trained in the same way that I discussed before, and the second of this network is trained for semantic facial part segmentation. And over here, what you do is the same kind of guidance that I talked about before. So you get the heat maps generated by the first network, and you stack them with the image, and then you pass them to the second network that produces the final segmentation masks. It's the same kind of trick, and And that's the results that we got. So this line over here is the yellow line is basically the unguided network. So this is what you would get if you just trained a network to do facial part segmentation. Then this line over here, which is purple, is the performance that you would get if you just took the landmarks produced by the face alignment network and connect them. Because as we said, you can do facial part segmentation by just connecting the landmarks of a face alignment produced by a face alignment method. And the orange is basically the performance of the whole architecture. Okay, that we proposed in that paper. And you see that if you guide the network with the landmarks, you get a large improvement in performance. Now, the blue line is a kind of upper bound in performance, and this is obtained by replacing the estimation of the landmarks from the first network with the ground truth landmark locations. Okay, so if we had somehow access to the ground truth landmark locations, we generate the corresponding 2D heat maps. We use them as input to the second network. You would get the blue curve, which is actually quite close to the orange one. I think this kind of idea shows the beauty which is in the simplicity of neural networks. Because, I mean, this kind of idea, take the landmarks and use them to guide facial part segmentation, is a fairly simple idea. And the implementation is also fairly simple. But if you didn't have this kind of architectures, if you didn't have deep learning, how would you do that? You would just have a vector of x, y coordinates, and somehow you have to use them to guide an algorithm that produces like dense prediction at the pixel level. So it looks simple, but if you try to do it in another way, it's not really that simple. Okay, so the last problem that I will be talking about is 3D face reconstruction, and that's a really difficult problem. So you are given like one, or in some cases multiple images of the same person, and you want to reconstruct the full 3D facial geometry. Okay. Now, computer vision methods really struggled before deep learning to approach this problem, and most of the methods would assume the availability of multiple facial images from the same subject, which is not always available, or they would work for simple images, little pose variation, good lighting, a little bit of expression, and of course they would require huge amounts of fine-tuning. Okay. So this is the kind of the state-of-the-art performance that you would get for 3D face reconstruction. That's from CVPR 2016. And that's without deep learning. Now, the setting becomes even more challenging if you have just one image in your disposal. So you have a two-dimensional image, you want to reconstruct the full 3D facial geometry. That's really hard, and the prevailing approach to solving this problem is basically the 3D morphable model, which was introduced a long time ago. This 3D morphable model approach is, you have basically a model for the 3D shape, you have a model for the texture, and then you want to fit the model to the image. You want to estimate the model parameters so that you would get a good reconstruction of the image based on the shape and the texture information. And to fit that model to the image, you must solve a very difficult, highly non-convex optimization problem. Okay? And that problem is really hard. You need to have very good initialization. So without good initializations, it won't work. Usually, 3D MM methods assume the ground truth for landmarks to constrain the fitting. And what else? So that was a difficult problem. And then with the advent of deep learning, what the community, the people thought about is basically to replace this very difficult optimization problem with some sort of CNN-based estimation of the model parameters. Okay? So this is work that was published at CVPR 2016 and also at this year's CVPR. And that's a really good idea. That works really well, a lot better than trying to solve this very difficult problem, a lot faster without this kind of fine-tuning or difficult optimization, parameter tuning that you have to do, high parameter tuning that you have to do for this kind of methods. And here you can see the result that you would get by a standard method for 3D MM fitting, and this is the result that you would get from this work, which was published at this year's CVPR. Okay. Now, what we thought that we could do to take this further is basically to completely bypass fitting or even building a 3D MM from first place. So, since the task is to produce some prediction at that lives in the 3D space, and since we already have architectures, fully convolutional architectures that can make predictions at the spatial domain, then we thought, why not try to directly train a network to regress the 3D facial mesh. So to make this work, you have to do a few things. So first is that it would be impossible just to take all the vertices of the 3D scan, like stack them in a vector, and then try to regress that vector. That would not work. So what we did was we took the 3D scan of the face, and then we placed it in a cube, and then we voxelized that cube. So we create a binary volume out of that cube. And whatever is inside the face takes the value of 1. What's outside the face takes the value of 0. Okay? And then, and that's the first thing. Then the second thing that we did, that's really important, this cube, this volume, must be aligned with the image. Okay? And because we can use like a scalar orthographic projection model, that's fairly okay. So there is no much of perspective distortion. You can do that for human faces. And then in the end, what the network does is to reformulate the 3D estimation problem as a semantic segmentation problem. So you have a two-dimensional image, and then basically you try to produce these 3D volumes which are also aligned with the image. So it's like reformulating the problem as a semantic segmentation one. So that will appear in ICCV, and let me show you some examples. So now with this kind of approach, which completely bypasses the fitting of a 3D MM, we can fit faces. We can produce the 3D geometry of faces in completely arbitrary poses, expressions, lighting, and occlusions. And as you may see here on the right, there is a large performance improvement over the CNN-based 3D MM approach. So that dashed purple line is basically a method that fits a 3D MM with CNNs. And all these curves represent the performance of variance of our method. And I also have some examples to show to you. Oh, you cannot see. Again, there is no tracking involved in this kind of videos. Each frame is regressed independently. And also, you can try your own face over here. So we are using a face detector that is good, but is not great. So let me choose. So this is Aaron, my student who did the work. So if I choose Aaron, so that's the face, and you can do this kind of stuff. Yeah. So you can try it on your own faces and see if it works. Get back to me. I was quite excited about this. He made this yesterday. So. Okay, now I have to. I don't have anything else to show to you, so I will close this. So I had a few slides to show you about face recognition. I will skip the slides and I will go directly to because the message does not really change. So, and that's my message. So, with large labeled data sets, face analysis, and well, I will not say computer vision, but face analysis can be solved. And basically, if we have this kind of data sets in our disposal, then it's a matter of time to come up with the appropriate architecture that will basically saturate the test sets in these data sets. Now the problem is not yet such a big issue with faces, because face is just a single object. People have annotated thousands of images. The real big issue is that labeling is costly. Okay, so to annotate an image with these 68 landmarks takes about 2 minutes. Okay, and there are like data sets consisting of thousands of images. So labeling is costly. In some cases, the problem is that you don't have the ground. You cannot get the ground truth. Okay, so for example, for this kind of faces, images collected from the internet, you cannot really have the ground truth for the 3D facial meshes. So normally you can get the ground truth for images, for faces that are somehow captured in the lab. You can have like a 3D scanner, you can get the ground truth. But how are you going to get the ground truth for this kind of images? It's impossible. So that's the problem right now. If we have a labeled data set with ground truth, we just go on, train a network, it will work. Or maybe we need to do some tweaks, come up with a better architecture, but guaranteed, people will find this. Because, there's not much that you can actually do in this kind of architectures. And that's my final slide. So what can we do? We can use, for example, unsupervised learning. Okay, so and that's some work from CVPR 2017. So very recent work. So you want to get the detailed facial geometry of the face. The coarse geometry, you can do what I just showed you. You can do this kind of volumetric regression approach. You can estimate it. You want to now do this for fine details. You don't have data. Okay. So what these guys did was basically to use a loss function, which is from shape from shading, to train a neural network. So that's the cost function for shape from shading, and basically if you have the albedo and the lighting, which you can estimate pretty easily, then you must adjust the depth, okay, so that this inner product over here gives you the image. So if you have these guys over here, the albedo and lighting, then the only other output that is required to the network is basically the image, which you already have. And in that way, using this unsupervised approach, you can just go on and train a network that will produce the fine facial geometry. And some of these results, you can see them over here. So that's really, really good idea. Okay, so at this point, I think that I will stop. And I am more than happy to take questions. Thank you.